like to introduce Alexandra Johnson. She's the AI product manager at Citrine Informatics. And welcome. The floor is yours.
Thank you. So I want everyone to think of a phrase that describes something that is really, really boring. Watching paint dry comes to mind. So does watching concrete cure. Now, I hope you won't use any of these phrases to describe my talk, but these are things that we often use to describe stuff that we don't find very interesting and that we'd rather not be involved with. But what if I told you that in 2019, the global paints and coatings market was worth $146 billion, and the global market for concrete and cement was $440 billion. These are big industries, and the next generation of materials that these industries design, like the paint for your house or the glass for your iPhone, is going to have an outsized impact on our environment, our economy, and the way we live our lives. And lucky for us, these industries are just waking up to the potential of artificial intelligence to design their impactful new materials. And that is exactly what I'd like to talk to you about today. I'm Alexandra. I'm an AI product manager at Citrine Informatics. At Citrine, we're working on building an AI platform for material scientists. I came to this field by way of computer science and machine learning. I got my BS in computer science at Carnegie Mellon. And then for previous to Citrine, I worked for a few years as a software engineer and tech lead at a small San Francisco-based machine learning startup. Now, I want to take you back to a simpler time, 2015, back when we could do things that today seem incredibly crazy, like host a cocktail party. In 2015, I attempted to host a cocktail party in which we were going to use AI to generate cocktail recipes. I went to a fancy liquor store in downtown San Francisco and learned about, what are the components of a great cocktail? They said it was alcohol, acid, sugar or sweetener, and water. So I got tequila, lime juice, simple syrup, and club soda, and invited friends over. Next, we had to configure our artificial intelligence algorithm. And we weren't using anything specific. We were just using general purpose optimization. So we had to set the bounds, like 1 to 1.5 ounces of tequila, like 0 to 1 ounce of lime juice. And then we started suggesting new cocktail recipes. It turns out that a 1-to-1 ratio of lime juice to tequila does not make a good cocktail, at all. It was absolutely disgusting. And so we tried doing things like, okay, maybe we can express this as a ratio of lime juice to tequila. We can hold the tequila strong. We can hold it constant, but then what about the ratio of sugar to lime juice or the ratio of sugar to alcohol? And, eventually we just gave up and looked up margarita recipes online and just called it a day. Our generic optimization algorithm didn't work, and we didn't know why. We were unable to adapt it to the cocktail creation use case. Fast forward to 2020 when I joined Citrine, and I am surrounded by folks with chemicals and materials PhDs. They know exactly how to express a problem like this. Turns out, creating a great cocktail is very similar to creating a high-performing paint. You have a bunch of ingredients. You pull ingredients off the shelf. You mix them together in different ratios and quantities. You kind of stir it up, and then you've got your new material. You've got your new cocktail. You've got your high-performing paint. And in chemical terms, this is called a formulation. And what Citrine had done is Citrine had developed a way to express formulations as part of their platform. All of a sudden, there was a language for expressing all of those things that I struggled with when I tried to use generic AI. And because Citrine had developed a language for expressing formulations, they could develop an algorithm that was fine-tuned for optimizing formulations. And as a product manager, this is my favorite part, they could also develop a user interface that was adapted to the users who are going to be creating new formulations. After learning about this, I was hooked. There's huge potential for verticalized AI for solving specific problems. And that's what I really want to talk to you about, the potential for chemical and materials aware AI solutions to materials design problems. In the rest of this talk, I'm going to walk you through a few challenges encountered during Citrine's years of experience bringing AI to materials design. And I want to show you solutions that have been shared with me by my generous and intelligent and kind coworkers that will hopefully have broad applicability to the physical sciences and beyond. This is the start of a typical materials project. This is a handwritten lab notebook. If you're lucky, then data is digitized, but that might mean something like it's scattered in different Google documents or PowerPoints that are just on somebody's, or like Word documents and PowerPoints that are on somebody's desktop. Maybe they'll have, maybe there'll be data in Excel, but generally you're working with something that's highly unstructured. And I mention this because, well, we all know we need to kind of like structure our data to get it ready for artificial intelligence. And so the first step of bringing AI to materials is often helping the user structure their data. Excel and SQL are good data solutions, but what are the components of a great materials data solution? A great materials data solution keeps all of the things that scientists love about lab notebooks and also manages to help avoid some of the pitfalls that they stumble on. Lab notebooks are super flexible. If you want to record extra data because it's a Tuesday, no problem. If your machine was broken and you had to use a different one to record some measurements and things are slightly different, just go write it down. No one's going to judge you. If you want to print out a photograph or a paper and staple it in there, like go right ahead. You can do whatever you want to with these lab notebooks. And that is really working for the scientists. So a great materials data solution should preserve this flexibility, whether it's being able to enter whatever fields you want or uploading things like images that may contain different media than just like classically structured data. Lab notebooks are a little difficult to use because often the second person coming in and reading a lab notebook sometimes can't quite tell what the first person meant. And this also comes up in Excel tables as well. You know, you said you measured transparency, but what wavelength of light did you measure transparency at? You know, I love cooking, so in like a baking example, oh, you're making bread. What type of flour did you use? Oh, this is all-purpose flour. Well, is it from King Arthur flour or is it gold medal flour? Because things like that make a difference in your final product. So a great data solution will include all of the context that, that scientists need to reproduce each other's experiments and to structure data together to get it ready for AI. Lastly, we know that any data solution that we come up with is not going to be as easy to use as a lab notebook. You're not just going to be able to like pull it off the shelf and start writing in it. And unlike me, not everyone likes structuring data just for the sake of it. So material scientists need some sort of incentive. Like why should they upload their data into this data solution? And besides structuring it for artificial intelligence, we have incentivized our material scientists to enter data into our data solution by allowing them to explore data relationships in a way that they would never be able to do in a lab notebook. They're able to view a material history diagram, which is a dynamic and interactive history of all of their process and ingredient steps that led to the creation of this material, thus incentivizing them to continually enter their data all the time, not just when they have an AI project coming up. And by building a data platform that is flexible, contextualized, and incentivized, and targeted towards material scientists and chemists, we were able to help our customers create an ecosystem of AI-ready data. Once data is structured, it's time to start searching for that needle in a haystack. It's time to start searching for that high-performing material that's going to do better than any material you've ever made before. And this is a very experimentation-driven process. So generally what happens is someone forms a hypothesis about what candidate might work, what might help achieve these amazing properties that we want in our new paint. And those hypotheses have to be verified. A real experiment has to be run to verify that we actually can attain the properties that we hypothesized we'd be able to attain. And unfortunately, this experiment often involves something like watching paint dry. These experiments can take weeks. They can cost tens of thousands of dollars. And they are time-consuming and expensive. So scientists want to make sure that they don't run too many. Enter sequential learning, also known as active learning in some fields. Sequential learning helps you search your space efficiently to find the highest performing candidate in your design space. And it is well adapted, and many of the kind of like methods of sequential learning that I'll talk about in the search strategy in step 3 will help you achieve better results faster than kind of like traditional having a scientist hypothesize and select candidates. First, you define a design space. So in the cocktail example, that's something like defining the bounds of your alcohol, the bounds of your acid, the bounds of your sweetener, and the bounds of your water. How much of each quantity am I willing to use? Next, you create a surrogate model. If you have training data, you can train a machine learning model on top of that. If you don't have any training data, you can set some priors over the field. Then you select a search strategy, and this is where you will see a lot of speed up. So there's kind of like, I think it was called something like grad student search, which is when a graduate student is the strategy for searching through the space. There is grid search, which unfortunately suffers from the curse of dimensionality as you start to handle more real-world problems in a high-dimensional space, as many materials design problems are. And then there's strategies that can help you search your space more efficiently, like Gaussian process back Bayesian global optimization, or we've found a lot of success with Monte Carlo methods. Next, you select the experimental candidates to run. The scientist fabricates those candidates, records the results, and then repeats steps 2 through 6, incorporating the data from their past experiments back into their model so that it can help inform what experiments they run in the future. And with a well-chosen surrogate model and optimization strategy, you can efficiently gather data and explore your space with less experiments than traditional like hypothesis or grad student-driven methods. But there's just one tiny problem with building that surrogate model. And that is that you may be literally parched for data. It is not uncommon for materials projects to have only something like 10 rows of data. We're just talking about how expensive these experiments are. Now, realistically, maybe you'll have something more like 100 if you can cobble together things from various data sources. But point being, we can't just throw this at a deep neural net. We have to, when doing materials design and when building that surrogate model, we have to find strategies that help us stretch our data further. And speaking of deep neural nets, so like we'd love to have 1 million rows and to just be able to like throw this all at a model and then have the model learn all sorts of relationships for us. But As we said, we don't have the data. But what we do have is we do have a bunch of domain experts who are our users. And I like to use this example of, well, my coworkers like to use this example of the Arrhenius equation. The Arrhenius equation is an equation that describes kind of reaction dynamics. So it can describe everything from crystal growth to chemical reactions in polymers. And if you provide a machine learning model with several hundred rows of data, then it can learn the Arrhenius equation. Or you could just like ask a chemistry undergrad to just tell you the Arrhenius equation, and you can encode it as a node into a graphical model. And my tech lead really wants me to make this point. When we talked about graphical models here, we're talking about a model graph, and we're not talking about probabilistic graphical models. So what our solution is to encode domain knowledge as analytic models within a larger model graph. And so we'll have one node to express the Arrhenius equation. All of the inputs to this equation may come directly from the data, or they might be predicted properties. And then the output is just the analytic output of the equation. We're done. And by encoding this domain knowledge into the model graph, we don't waste data relearning a relationship that a scientist can just tell us. Speaking of scientists, our users are scientists. Our users are material scientists and chemists, and they often have PhDs in the field. They have years of domain expertise, and they have a lot of experience. And up until now, this experimentation, this materials discovery process, has been something that they've completely owned. It's often their intuition and their analyses that are suggesting what candidates to run. And they get to sit around and collaborate when they're deciding on what experiments to run next. And it isn't our goal to replace them. It's not our goal to just tell them what experiment to run next, just run this one, run this one, run this one. We want to involve them in the process. Like we did with domain knowledge integration during graphical models, we can involve our expert in the candidate selection process with uncertainty quantification. All physical processes are inherently unstable. Think of trying to bake cupcakes and think of how every cupcake that you bake has it looks slightly different. And even experts who are making millions of gallons of paint every year cannot fully remove all of the uncertainty from their data. Also, our model is not going to be highly accurate. As we said, we're sometimes working with only 100 rows of data. And so we're not going to have a highly accurate model. Uncertainty quantification exposes all of this to the user. Instead of just saying, what candidate do I run next? We show the user a list of top N candidates. And here, N is going to be somewhere in the hundreds. And each one has an uncertainty score. And through that, we allow our user to get involved in the process. Our user can see where are we suggesting a high-performing material that we're really certain about, and where is our model kind of thrashing around a little bit. Our user has everything at their fingertips to make data-driven R&D decisions and to say, no, this is the area that I want to learn more about because I want to be able to build models that perform better here. Or I'm ready to start exploiting. I want to fabricate this high-performing model. And so the scientist becomes this human slider between exploration and exploitation. And there's a quote from a KDD Dash paper that I really like that I think captures what we're trying to do here. The kind of question to ask yourself when designing interfaces for scientists is, how might we design to support exploration, learning, and in turn, enrichment of their expertise? And our way of doing that is through uncertainty quantification. Now, this talk started out with the impact of materials and chemicals and the opportunities for AI, and ended with some practical solutions for common challenges one might encounter when bringing AI to materials design. Data is messy, and a great data platform helps material scientists create an ecosystem of structured data. Experimentation drives materials development, but it's time-consuming and expensive. Sequential learning, with a well-chosen search algorithm, can help us efficiently search our space. Data is scarce, and smart use of graphical structures, such as encoding domain knowledge and analytic models, can help stretch our data further. And finally, the user is a domain expert, and we can enrich their expertise through providing them with uncertainty estimates during human-in-the-loop candidate selection. Now, I hope you walk away with some ideas to use in your own work, and that you're more inspired to learn about materials and chemicals. Got some resources that they'll be providing on the MLconf website. And if you are super inspired to learn more about materials and chemicals, we're hiring. Citrine is hiring across data science, software engineering, product management, research engineering, and we'd love to talk to you if you're interested. So check out citrine.io/careers to learn more. Otherwise, thank you so much for having me, and I can take a few questions.
Thank you, Alexandra. Are there questions for Alexandra? If there are no questions, this is the last speaker on this track. We invite everybody to attend or move over to track 1 for the startup showcase, which starts at 4:15 Pacific time. Alexandra, thank you so much. It was very interesting.
Thanks for having me.